take a syringe, maybe from a kid's medicine bottle, and you put your finger over the end and try to push the plunger? You feel that resistance, right? That pushback? Well, let's get into that, because what you're feeling is actually a fundamental law of physics in action.
So what is going on in that moment? I mean, yeah, you're squishing the air into a smaller and smaller space, obviously, but something else is changing inside there, something you can't see, but you can definitely feel. We're talking about pressure, and it has this kind of secret relationship with the space it's in.
To really get this, we've got to talk about a simple but super powerful idea. I like to call it the opposite rule. And once you get this, you'll understand exactly how gases behave whenever they're squeezed or when they're allowed to just expand.
This right here, this is the whole game. It's what's called an inverse relationship. And all that means is when one thing goes down, the other goes up. It's like a seesaw. So when the volume, that's just the amount of space the gas has, when it goes down, the pressure shoots up. And if you give the gas more volume, the pressure does the exact opposite. It goes down. They always move in opposite directions.
Now, this opposite rule has an official scientific name, Boyle's law. It's just a more formal way of saying that as long as you keep the temperature the same, a gas's volume is inversely proportional to its pressure. It's exactly what we were just talking about. Squeeze a gas, pressure goes up. Give it more room, pressure drops. Simple as that.
And of course, scientists have a neat little formula for this. But don't worry, this isn't going to be a math test, I promise. All this says is that the pressure times the volume you start with, that's your P1 and V1, is always going to equal the pressure times the volume you end up with. So if you cut the volume in half, the pressure has to double to keep both sides of the equation equal. It's all about keeping things in balance.
Okay, so we know what happens, but why? Why does pressure go up when you shrink the space? To get that, we need to zoom way in and see what the individual gas particles are up to. Let's imagine we're all invited to a particle party. So just picture the air, or really any gas, as being made of billions and billions of little particles. Think of them like tiny ping pong balls. And these things are not just sitting still okay. They are zipping around like crazy, bouncing off each other and smacking into the walls of whatever container they're in. So here's our party. In a big box, the ping pong balls have tons of room to move. They're all spread out, and they don't hit the walls all that often. That's low pressure. But now let's move the party to a much smaller box. Suddenly, everyone's crowded. It's shoulder to shoulder. They have nowhere to go, so they end up slamming into the walls way more often. And all of those extra hits, that creates high pressure.
So that's the absolute crucial point, right there. A smaller space forces all those particles to get cozy, and that directly leads to way more collisions with the walls of the container. And what is pressure? It's just the force of those collisions. So more collisions literally means higher pressure. It's a direct cause and effect. Okay, cool. But what does this have to do with anything in the real world? Well, it turns out this isn't just some abstract science concept. It is happening all around us, and even inside of us, every single second of the day. I mean, just think about breathing right now. As you inhale, your diaphragm moves down, your lungs expand. That's an increase in volume. So, what does Boyle's law say happens to the pressure? It drops. The pressure inside your lungs becomes lower than the air outside, so air just rushes in. Then to exhale, the opposite. Your lungs shrink, volume decreases, the pressure inside skyrockets, and the air gets pushed right out. You are a walking, breathing example of Boyle's law. And it doesn't stop there. That syringe we started with, classic example. Squeezing a balloon, you can feel the internal pressure build as you make the volume smaller. And for scuba divers, this law is a matter of life and death. As they dive deeper, the incredible water pressure around them compresses the air in their tanks and their bodies, and they have to know how to manage that. It's serious business.
Now, like any good rule in science, Boyle's law has some fine print. It works perfectly, but only if you follow a couple of conditions. So let's quickly go over the rules that make the opposite rule work.
There are two big ones. First, the temperature of the gas has to stay the same. Why? Well, if you heat a gas up, its particles start moving faster all on their own, which would increase the pressure and totally mess up our simple volume-pressure relationship. Second, the amount of gas can't change. You can't have a leak, and you can't pump more in. If you change the number of ping pong balls at the party, that's obviously going to change the number of collisions, right?
So look, if you take away just one single thing from all this, let it be this. The whole idea of Boyle's law is incredibly simple but powerful. You squeeze a gas, its pressure goes up. You let it expand, its pressure goes down. That's it. That's the opposite rule in action.
All right, so now that you know all about this inverse relationship, I've got a question for you. If you take a sealed container full of gas and you magically double its volume, what happens to the pressure inside? I'll let you think about that one.